A very good morning to all of you. I hope the slides are visible and the audio is clear, right? So I will be starting the session by 11:20. So wait for 2 minutes. I will be starting the session by 11:20, okay? So before starting, I will be telling you few points. I hope the audio is clear, right? So any of you can just text me whether it is audible or not. I hope it is clear from my end. I will be starting the session by 11:20. Just wait for 1 minute. I will just start it by yes, Moinak, thank you for your response. It's already audible and visible. Thank you. Okay, so it's already 1:20, so I will be starting the session on the computer organization and architecture, and it is based on the basic GATE syllabus that is going to be covered during the session. Okay, so before coming to this one, many of you, I will not say many of you, 2-3 of you have asked me how to get a good score in GATE, right? So the thing is that I will not tell too much of Gyan, I will not tell. So the thing is that you have to be a bit strategic. Okay, now if you see the syllabus, the major chunk of the syllabus is having the mathematics part. You have the digital logic and the COA section. Okay, and okay, thank you for your response. It is clearly audible. Okay, so digital logic you are studying. NB sir is telling that is he is just giving you the lectures on the digital logic and COA. Apart from that, you have this DBMS, right? And in the 6th semester you will be having this computer networks. The GATE syllabus will be covered in the 7th semester, like the 4th year students. So already you are getting the opportunity to grab the or to totally habituated with the digital logic, COA, and the algorithm data structure also you have studied. So you have the opportunity to get the marks, but do not go for remembering or all the subjects. Okay, for especially at the 1 month before the GATE or 2 months or 3 months before the GATE, we actually, from my point of view, what I did, I selected 5 of the subjects which I preferred the most. Okay, all the subjects I will study, but 5 to 6 as per your convenience you will select the 5 to 6 subjects along with the mathematics also. ठीक है, तो तारपरे जेटा करबो जे main thing is that you which papers are giving much more marks, that weightage also you have to find out. So last 5 to 6 years of question you just go through, see which chapters are giving, they are giving more weightage. This is very very important. Okay, we are studying and we will get the or we will crack the GATE exam. It's not like that. You have to be a bit strategic, okay, when you are going for the exam. So if you are comfortable with digital, you go for that. If you are comfortable with data structure, you go for that. Out of 5, right, there are basically 9-10 things are there. Okay, anyways, so for my part I am telling you, I will be starting from the very beginning. Okay, I do not know how much it has been covered, so it's better to start from very beginning. It's a machine instruction, and that is the instruction set I will be covering. Okay, instruction set I will be covering. Okay, so let's talk about the planning that I have done today. I will be discussing the basic theory and I will be solving 4 to 5 problems. Okay, so this is the mode of agenda today. A bit introduction of the theory along with the problem solving. Otherwise it is very difficult to crack the GATE without the problem solving part. Okay, so and I will prefer to give the GATE related problems only. I have not given any other problems, which the GATE problems which came in previous years, those problems only I have given. Okay, so let's start with the presentation now. So these are the thing, right? You know this thing, but a little bit of brush up. So the instruction set, you can differentiate the instruction set on the following basis. These are the points the designer is concerned about. Okay, when they are designing the instruction set, they are mainly concerned about the things: the number of bit per instruction. Now whether the instruction is stack based or register based. Okay, number of explicit operands per instruction. There are different types of instruction, you know, right? So whether the number of explicit or implicit, the number of operands are there, and the location where it is stored, whether it is stored in the memory or whether it is stored in the register, that also very important. Just wait 1 minute. Okay, so whether it is stored in register or whether it is stored in memory, that is also important. Which type of operation you are doing? You are doing addition, subtraction, multiplication, comparison. Okay, lots of types of operations are there, and the size and the type of the operands. Okay, so there are different types of operand. Let's come to the next thing. Okay, so you have the instruction set. See, the theory part I am not giving too much of time. Okay, so I will be quickly covering the slides. I am not giving too much of time. If you have any query, you can just text me. Okay, so this is known to you, that's why I will not give too much of time for explaining it. Okay, so instruction set architecture are basically measured the memory space. Okay, the instruction complexity. We will prefer the instruction which will be easier to implement, right, which will not take too much of time. The instruction length in terms of bytes and the number of instruction. Okay, and if you go for the instruction formatting, these are the few points that you need to remember. Okay, what are the few points? You can see the instruction length, the number of operand, addressable register is also very important. Okay, and you have the organization like byte or word addressable, which one is preferable. In the gate question, if you see some question, these terms are there: byte aligned fashion, the instruction are stored in the byte aligned fashion. These terms, like another term we will be hearing like register spelling. Register spelling, what do you mean by register spelling, or what do you mean by the byte aligned fashion? These are the certain terms in gate question they will be using. Okay, I will be explaining all these things when I will be covering the question answer session. Okay, and the addressing modes, you know, there are 10 types of addressing mode apart from this one. Okay, so there are addressing mode, I will be taking another class for addressing mode. Okay, now in case of instruction format, you can see there are two types of ordering, rather you can say the byte ordering, and that is known as the little endian mechanism and this big endian. How you can differ it? See, from this type you will be getting not the numerical type question, you will be getting like different type of question that is apart from the numerical one. Okay, you can see the question paper. So the thing is that if you give one example here, it will be clear for you. So in little endian mechanism, you have the least significant byte followed by the most significant byte, and for big endian you have the reverse thing, right? So if you have the example like 1 2 3 4 5 6 7 8, okay, so you are arranging this one in terms of the big endian or little endian fashion. So the LSB is this one, right? So this one is, so the byte ordering fashion, so this one will be written first, then it is coming to 1 2. Okay, this is the from LSB to MSB, this is the way these are arranged. Okay, and in case of the big endian fashion, it will be from MSB to LSB, the way the last explanation was given. Okay, so these are the nominal thing. Okay, now which is important is the instruction set. Okay, instruction set, you know, is basically the collection of instruction that is understood by the CPU. Okay, these are the instruction. How many types of instructions are there? Few things that is very important as far as the exam is concerned. Many of you have given the exam, right? So you know all these things previously. Still I want to just brief you one thing. The instruction length is very important, and the length of the instruction can be affected by the effects of memory size or memory organization or bus structure or CPU complexity or CPU speed. Okay, and another type of question they used to ask you that how many minimum number of registers that are required. They will give one expression and they will ask you that how many minimum number of registers that is required to implement that one. Okay, so you require to implement that one with optimal number of registers. Suppose you have already done the expressions like something a plus b minus c plus d, that is one expression. You have used the 3 addressing instruction, 2 address instruction, like different things you have done, right? So which one is the better one with minimum register, that you also have to think of. Okay, now for any kind of instruction actually you require 3 things. You know this one, opcode and the operands. There may be one source of operands or multiple sources of operands, and the result will be stored in one of the register or memory somewhere. Okay, you are doing something, okay, to which you are doing this, and you are putting the answers in some of the values. Okay, some of the register values. Okay, now the register, that is the registers or CPU or IO or whatever is the thing, is that they are capable of storing the operands. Okay, these are the places where the operands can be stored. Okay, that also in the gate question they will mention that only register can be capable of storing it. Okay, you have to reuse the registers. Okay, that type of question will also come. Now the thing is that we generally prefer 4 instruction format. Is it true? No, we prefer, what are the things? We can prefer that 1, 2 or 3 operand addresses, because the 4 operand addresses are not used too much due to its complexity and the long instruction word. This is the reason, that's why we always prefer that 1, 2 or 3 operand addresses. Okay, so I will share the PPT, the thing you have. So this is the example mostly you have done in your textbook. It can be Hamacher or it can be Hayes or it can be TK Ghosh, whatever the book you prefer, you can go through. So in case of 3 operand instruction, what we can find that there will be 2 source operand and the destination operand. These are the very important 2 source operand and you have the destination operand. I will be coming to the gate questions after this portion is over. Okay, now if you go for this example, you can see I am keeping the pace a bit low now. If you have the expression like this and you are using 2 source operand, and so ultimately 3 operands you are using. Okay, now in the instruction, this is the opcode, you know, this is one operand, this is another operand, and this is another operand. 3 operands you are using. Okay, so what you are doing it here, to implement this instruction or the sequence of instructions is to be written. Okay, so how you are writing this one, you are calculating this one first, the subtraction which is within the bracket. Okay, you are keeping this result within the R1. So this is the destination one, right? This is the destination one where you are keeping the result. What is the result? Result is basically the difference between A and B, that we have done here. Next, you are making the product by multiplying D with E, right? And you are putting this product in another register. So this is the second another operand register where you are just you are putting the product, and this MUL is the opcode. Okay, third one is that you are adding this C with this one. Okay, when you are adding C with this one, you are using another opcode like add. Then what you are doing, you are just adding the C with the content of R2, because in the R2 content what was there, D into E was there, right? So whatever is the content of R2, that will be added with C, and ultimately you are getting the final result by dividing this R1, whatever is the R1 is there. What is R2? R2 is nothing but C plus D into E, right? So you are dividing this R1 content, that is A minus B, by whatever is the content of R2. R2 contains this whole thing and R1 contains this one. So you are just dividing this one to get this final Y expression. Okay. Now this is all about the 3 operand instruction. Now if we go for 2 operand instruction, we are cutting down the number of operands. Okay, we are cutting down the number of operands, and what its advantage, we are just overwriting the old data with in the location. Okay, we are overwriting the thing. Okay, so we will be using the same expression and see how we are solving. I hope you have studied this one in the last semester. Still a little bit of brush up. Suppose you are using here also, which operation you are going to do, the A minus B operation you are going to do first, and this operation, the result of this operation is going to be stored in the A itself. Okay, A itself. Now you are doing the product operation, that is going to be stored in D, and you are using this one and this one. Then whatever is the resultant, that is, it is the product is stored in D, right? So when you are adding this with C, what you have to do when you are adding this one with C, so actually you are just putting this instruction add D comma C. So whatever was the content of D, that will be added with C. So D contain D into E, right? So now D is not D. D contain D into E. So it will be containing ultimately D into E plus C. This D will be containing D into E plus C. So you obtain this portion. Okay. So you have this one. This one is contained by register A. Okay, and you have this portion is contained by register D. So if you divide A by D, you will be getting the final expression. Okay, so here you can see you are using only 2 operands. Here only 2 operands are there. Previously you had the 3 operands. Okay, now 1 operand instruction, you know, we will be using this DLA, that is the store or load accumulator, like this type of instruction we will be using. And the thing is that we are reducing the size of the instruction. Okay, we are reducing the size of the instruction. And for 0 operand we have which one? You have the stack based. Okay, you have the push, pop, and then add will give you whatever the upper 2 values, they will add it and they will push back into the position. Okay, so this is the thing, and they use the LIFO sequence. LIFO means last in first out. This is the primary things. I am not explaining in detail because you know. So 4 types of operand, 3, 2, 1 and 0 operand instruction. 4 types of operand instruction we have studied. Okay, so this is the example of stack based. Now come to the question. This is our aim. Okay, now when we are coming to this question, we will be solving this one slowly one by one. So this question was asked in GATE 2017. Okay, so I will be using the whiteboard along with this. Okay, so let's okay, so you have this one. Just wait. I think it is visible, right? I think it is visible. Okay, so consider the expression. They have given one expression. Okay, they have given one expression, and the expression is this one. The expression is this one. Okay, this is the expression they have used. This is the expression, a minus 1 into this one. Let's read the question carefully. Consider the expression this. Let x be the minimum number of registers required by an optimal code generation without any register spill. Okay, algorithm for load store architecture. Fine. The number one point they told that only load and store instructions can have memory operands, and the second point they told that arithmetic instruction can have only register or immediate operand. They are asking you what is the value of x. What is x? They are asking the x is the what is the minimum number of register. Whether it requires 2 register or 3 register or 1 register, what is the minimum number of x is what? That is the minimum number of register that is required. Okay. So now when we are going to solve these types of problems, so we will be writing the expression. Okay. So let's write the expression. The expression is a minus 1, okay, into, you have, I am not writing too much of bracket here, I am writing simply b plus c divided by 3. Okay, I am keeping this bracket here, plus d. Can I write it in this form? Okay, so I can write it in this form, right? So when I will be writing like this, okay, so what can I do here? Basically you have one memory, and within the memory block you have this a, b, c, all the stored things are there, right? So because you will be using a, b, c, d, all the things are there, and you have to load and store architecture. You have to load it from memory. Okay, only load and store instruction can have memory operands. Okay, so these are a, b, c, d are stored in the memory. Now I am writing in this fashion, I can load it, right? So the thing is that I can, suppose I am using one register R1. Okay, so I can load this register R1 with the a value. Okay, and or you can say you can load this R1 with the b value. Just do it slowly. Okay, I can load this R1 with the b value. Okay, this one, because it is within the bracket, right? I will be solving this one first. So I will be solving this one. So I am loading the R1 with b value. Okay, and what can I do? I can load the another register I can take with the c value. So what is our intention? To make this one b plus c. Okay, so when you are doing this b plus c, okay, so what can I do next? I can add this 2, right? So I can add, because I have to write the full instruction, and how much number of register that is required, that I have to find out. Okay, so when you are solving this one, we will be solving, right? R1 comma R2 is basically the solution to add this b and c. So what you are getting here, actually ultimately what is the meaning of this? R1 এর মধ্যে কি আছে? R1 এর মধ্যে you have this R1 plus R2, right? So what is the meaning of that? Within this you have this b plus c. Okay, now this is done. Okay, now what is the next step? You have to do the division part. So what you have to do, you will be writing this div, this value you have to divide by 3, right? So whatever is the value of R1, that you have to divide by 3. That you have to divide by 3. If you are going to divide it by 3, what the R1 will contain? The R1 will contain this R1, whatever was the previous value, by 3. That is what? That is basically b plus c by 3. That will be contained by this R1 now, after this division operation. Okay, now when we are thinking of this part is over, when what you have to do? We have to do this addition with the D operand. Okay, so what you have to do, will you take another new register? Will you take another new register? See, only I am using this R1 now. R2 is vacant now. R2 is having C, but C is not used anywhere now. So we can reuse the R2. So I will be reusing the R2. I will not take any new register R3. Okay, I will not take any new register R3. Your question is, that is AX, you have to calculate the number of, or you can say the minimum number of registers that you will require to implement this equation. Okay, so when you are doing this one, you will be having this R1 which will be containing B plus C by 3. So D value where you are going to load, I will be loading this D value in the R2 itself. In the R2 itself. Okay. Can I do it? In the R2 I am reusing this one. So if I write it in this fashion, so R2 value will be what? R2 value will be, can you tell me what is going to be the R2 value? So R2 is basically having this value D now. Okay, so this is up to this. Now this part is, now you have to do what? You have to add this one with this D. So what you will be getting now? So you have to add, just 1 second. Okay, now what I can do right now here, see, up to this it is clear, right? So when you have this part, it is R2 part is done. Now what I have to do, I will be loading, this one is done, so I will be adding this R1 with R2. Why we are using this one? Because R1 is containing B plus C and R2, not B plus C, B plus C by 3, and R2 is containing D. So when you are doing this one, what you are ultimately getting, R1 will contain R1 plus R2, right? So basically this will be containing what? D plus that B plus C by 3, that whole thing will be contained in R1. Done. Now what is the next step? Up to this you are only using 2 registers. So this part is done. This part is done. So again I have to bring one other variable A. So see, here only R1 is getting used. R2 is again we can reuse R1. Okay. So what we can do it here, we can just load the A value in again R2. Can we again put the value of A in R2? Because only the resultant part is stored in R1. So R2 we can load with again A, right? So when we are doing this, what is the resultant you will be getting? You will be getting just R2 now contains the A value. Okay. So when you are going to get that one, what is the next step that you will be having? You will have to do what? You have to just subtract this. You have to subtract this A value because you have the another portion A minus 1, right? So you have to subtract the A value by minus 1. So what you have to do, the whatever is the R2 value, you subtract it 1. So now R2 will contain what? A minus 1. Okay. So this is done. So A minus 1 you are getting in R2. And the remaining part you are getting in R1. Okay. Now what you have to do, if you just simply multiply this R1 comma R2, you will be getting what? R1 will contain this A minus 1, that is R1 value, into this B plus C by 3, that is this part, right, plus D, this part. So ultimately how many registers you required? How many registered you actually required? 2 registers, that is R1 and R2. Only 2 registers you required, because you have utilized or you have reused a register R2 multiple times. Why you have reused? Because every time when we are using, we have to check whether that variable is required or not. Okay, D was not required, that is B plus C was not required, so we have replaced this one, right? So every time, so you require x equal to 2 thing to implement this value. Is it clear to you, or I have to repeat once again? So this is the base. So if the question is something different, I have solved it one by one step by one step. I think you can do it, and this type of question used to come, so please try to solve this type of question. Okay, now you see the next question. Next question is based on this one, right? Registers and instructions and all these things. Okay, I'm just copying this one. I hope it is clear to you, right? It is visible. I hope the thing is visible to you. Now, see the question. The question shows you that consider a processor with 64 registers and an instruction set of size 12. Okay, each instruction has 5 distinct fields, namely opcode, 2 source registers, okay, 1 destination register, and you have a 12-bit immediate value. Okay, so each instruction must be stored in memory in byte oriented or byte aligned fashion. This is the thing I told you at that point of time, byte aligned fashion and all these things. What do you mean by byte aligned fashion? Those, so each of the word value is 8-bit, or so it will be stored in the 1 byte by 1 byte. This is the way the instruction will be stored. Okay, and if the program is having 100 instructions, the amount of memory in byte consumed by the program text. Okay, so this is the thing. Now before starting this one, I would just like to just tell you one thing. If we think of this value, this so if you think of this value 64 registers, okay, so what do you mean by this? Just for sake of understanding, if you have a stack with 64 registers, that means 1 2 3 4 up to 64 registers are there. Okay, so definitely each of the register will have some address values, right? What is the address value and how much bit is required to show the address values? How much bit is required? So you know there are 64 combinations. So 64 combination means 2 to the power 6 number of combinations, right? So each of the, so 2 to the power n, and n is the value that denotes the number of bits. So 6 bits are actually used as the address of the each of the register. I hope this understanding is clear. That means if you have a 64 register in your processor, so each of the register address is having 6 bits, right? So this is the thing. Now this is one thing. Now if you have an instruction set size 12, can you tell me what is the number of bit that is represented, that is used to represent the address of each of this? So 1 2 3 4, how many number of, so if you have this, I am talking about this one 12, So 1, 2, 3, 4, up to how many number of instruction sets or instructions are there? There are 12 instructions are there. I am talking about instructions, okay, and this is about the register. 12 instructions means 12 is what? 12 is basically less than 16, and that is 2 to the power 4, right? So I can say each of this instruction, the register, that is the address of each of the instruction will be how many bits? 4 bits, right? Is it clear to you? Okay, so I am just erasing this point because this is for your understanding only. Okay, now just keep it here with this. Now the question you just see from here, each instruction is having 5 fields. Okay, when we are talking about each instruction, how many fields are there? It is having 5 fields. So if you have one instruction here, it is having 5 fields. Okay, 1, 2, 3, 4, 5. Now the first field, just check here, the first field value is what? Okay, the first field value is what? It is basically the opcode. You just check it, it is the opcode, then 2 registers and 1 destination registers. So this value is basically the opcode, right? This is basically the opcode portion. Then you have the register 1, source register 1, source register 2, and you have the destination register, and you have another immediate value. You can see the immediate value, and what is the bit? This is the immediate value. So what is the bits of this? You can see the opcode, how many bits it will take. Can you please tell me how many bits it can take? Because opcode means it is the set of instructions, right? It is the instruction, right? So each of this opcode you can take how many bits? It will be there. It will be there 4 bits, right? So 4 bits will be there. Then register R1 registers are there, 64 register, and the address of each register is you got it 6. So this is also 6 bits. This is also 6 bits. This is also 6 bits, and this is the thing that is 12 bit. This is given in the question. You can see this is a 12 bit immediate value. 12 bit immediate value. Okay. Now the thing is that if you think about the total instruction, what will be the total number of bits for each of the instruction? Okay, so you can calculate the total bit. How will you calculate the total bit? You have the 4 bit for opcode, 6 bit for the source register, another 6 bit for the another source register, 6 bit for the destination register, and you have the 12 bit for the immediate value. So if you calculate it, this will 18 plus 12 is basically 30, and 4 it will be 34 bits, right? You will be 34 bits. Now when you are solving this one, you have to see one thing. The point that I wanted to focus, the memory, each instruction. So each instruction requires how many number of bits? 34 number of bits, and each instruction must be stored in the memory in a byte aligned fashion. Now if you think of a byte aligned fashion, suppose you are learning the microprocessor and all these things, right? So when suppose you are storing in the microprocessor address, you have this storage, right? So you have the address field like 8000, you are storing one thing, then 8001 you are storing another thing, like this is the way you are storing. So how many bits are there? And you can say this is byte aligned, means it is 1 byte. The length or the word length is 1 byte. So this is basically 1 byte, right? That is 8 bits. Okay, so this, how many total bits are there? 34 bits are there per instruction. So these instructions to be stored here. So here 8 bit, 8 bit, 8 bit and 8 bit. So 8002 and 8003, stored. Now you have another 4 32 and now 34 means 8004 you have 2 bits. So how many bytes you required to store 34 bits? How many bytes actually you require? Because the 6 other bits are basically vacant. You cannot store anything here, right? So actually ultimately 5 bytes of capacity actually or memory you require to store one instruction, because one instruction you obtained it is 34 bit and 34 bits are aligned in the byte fashion. So 18888 and last bit is 2. Okay, jodi eta if it could have been like another 8, so it will be like সেটা যদি 40 হতো তাহলে এটা হয়ে যেত another 8. So if it is 34, fine, we can take it 2, and but the memory requirement is 5 byte. You cannot deny with that. Okay, so if you have this 5 byte, so the total, so you have the 100 instructions, right? 100 instructions you have. So for each instruction, so as you know this, for each instruction you require the 5 byte. So how many instructions are there? 100 instructions are there. So 5 into 100, that is 500 bytes are actually required. So what is going to be the answer? So the memory requirement or the total memory requirement to store those 100 instruction will be how much? 500 byte. I am repeating once again the question. You see this one. This is the amount of register you have. From this register value you are just 64 register. That means 64 means 2 to the power 6. Each address of the register will contain 6 bit. Done. Then you have the instruction set which contain 12 instruction. That is 12 is less than, I should write it properly, actually this is basically 12 I wanted to write. Okay, so 12 is basically less than 16, so 2 to the power 4, so n is 4. So each instruction, the address of the each instruction will contain 4 bit. Okay, and you know you have the opcode which consists of the 5 fields, the opcode, 2 source value, 1 destination value and 1 immediate value. So opcode source address value, you know that it is 4. You obtained from here. The register values are 6 and 6. 3 register values are 6 because 6 bits are required for each of this, and immediate in the question it is given 12 bit. So total number of bits required to implement is 34. Now as the memory is using the byte aligned fashion, that's why you are using this 8 bit and this 2. So total one instruction consists of 32 bits. Okay, so as it is the 32 bits, but you can say ma'am the rest bits are not required, right? These are vacant, it will be wasted, there is no other option. So ultimately 5 bytes of the memory will be required to implement one instruction. So if one instruction requires 5 bytes, so you have a program of 100 instruction, it will be requiring 5 into 100, that is 500 bytes. I hope I made it clear, right? So this concept we will be utilizing for the next question also. Okay, now see the next question. Okay, so see the next question. I'm just copying this one into my, otherwise it is very difficult to every time just look into this. I hope it is visible, right? Okay, so a machine has 32-bit architecture. A machine has 32-bit architecture. This is the third question I am giving you. I hope you can solve this one and you can send me the answer if you, this is a similar type of question but a bit twisted, because unsigned range, I do not know whether you don't know it or not. A machine has 32-bit architecture, that is 32 bits are stored, okay, and each instruction is one word, okay. So 64 registered, see this type of question I told you earlier also. 64 register means what? 64 register means basically again the same thing. If you have 64 registers, 64 register means what? 64 register means what? You have 2 to the power 6, that is each RS address, I can say, will contain 6 bits, right? So this is the thing. And if you have the thing, right, and in each of the instruction will be containing this one, immediate operand and 2 register operand. This is given. So what is the structure of the opcode? What is the structure? How can we draw this one? As per the question, we can draw it in this fashion, right? How can we draw it? So we can draw it in this fashion. From the question itself, it is known as the immediate operand and additional 2 register operand, okay. So when you are having this 2 register operand, opcode is primarily required. Opcode is mandatory. So you require this opcode. You have this 2 register operand, right? You can say R1 and R2, and you have this immediate operand that is also there. Now if you have this one, you can say, see this one, 64 registers each with 32 bits. So actually if you have the instruction, if you have this 1 2 3 4, you have to visualize, otherwise it is very difficult to understand, okay. 64 registers, if you, so you have 0 or 1 to 64 you have, so each address is going to be 6 bit. Along with that you have this, how many long? The long length is basically 32 bit, okay, basically 32 bits. So it is given there. Now so opcode, how many number of bits are required to represent opcode? You see 45 instructions are there. So 45 instructions are there, 45 will be less than what? 64, right? Taito. And if you have 2 to the power 6, so for opcode also you require, so this is for the instruction I am calculating, and this is for the register I am calculating. You have to calculate the bits, right? So you have, for opcode you have 6 bits, for registers also you have 6 bits and another 6 bits, okay. And you have to actually, you do not know this, because in the previous question it was given 12-bit immediate, but here in this question they have not given 12-bit or something. What is the value of the number of bit? They have not given. So when we are using this one, we know one thing extra from this, the total bit, how much is the total length of this one, that is given to the question, okay. So if you have this question, is 32 bit, right? So you have the 32 bit architecture, that's the instruction will contain 32 bit, okay. So you can calculate what is the value of like y or something like that. So y can be calculated by 32 minus of this 6 plus 6 plus 6, okay. So your question is, you have to maximum value of the immediate operand. What is the maximum value? So you calculate y first. If you calculate y, it will give you 18 and it will give you 14 bits, okay. So you calculated this as 14 bits. How you calculated? You know from the question, that is 32-bit architecture, so this will be 32-bit, and actually you are subtracting these values 666 from the 32 and you obtain this one. Now this is not the answer. your answer is, assume the immediate operand is an unsigned integer. Okay, the maximum value of the immediate operand is what? The maximum value of the immediate operand is what? Now I am giving you one example. Suppose you have the AB operation. AB, you have 0 0 0 1 1 0 1 1, 2 bits. Suppose you have 2 bits. Then I will come to 32 bit. If you have 2 bit, the values can be, if it is unsigned, 0 1 2 3. That is 3 is the maximum value. If the range is 2 bit, then this much of combination can be possible, and the highest value is 3. 3 ke amra ki likhte pari? 3 can be written as 2 to the power 2 minus 1. Can we write it? So we can write it. So the range of the unsigned, or the maximum value of the unsigned, will be 2 to the power n minus 1. N is the number of bit. Then, so how many number of bits are there for this immediate part? For immediate part you have 14 bits, right? As you have 14 bits, so can I write the range? The range will be, for this case, for example, for 2 bit you have this 3 and this one, right? Now for in case of 14, what will happen? So in case of 14, what will be the maximum value of the immediate operand? So it will be like 2 to the power 14 minus 1 will be the maximum value. Is it clear to you? So when we are talking about the maximum value, whatever is the bit position, if it is unsigned, definitely if it is unsigned, because unsigned, suppose there are 3 bits. 3 bits, how many value? 0 to 7. 7 ke kibhabe pai? We can find 2 to the power 3 minus 1, the 2 to the power n minus 1. 0 to 7, that is the 3 bit maximum value, right? 7 is the maximum value. So similarly, if 14 is the maximum, so 2 to the power 14 minus 1 is the maximum value of the immediate operand. Okay, so this is the type of question that it will be that used to come here. Okay, so we can be solving this one, and you have another problem, you can solve it here, and you can text me if you have any problem out of it. Okay, so please try to solve this question. This is another type of question from instruction set. You solve this one, and if you have any query, please just text me how you are going to solve it. I am giving you the hints of solving this one. I am giving you the hint of solving this one. Okay, how will you solve this one? So there are 4 types of categories of registers. Okay, for each of the case, or for 64 you have register for floating point and 16 integer register. So from 64 you can find out how many number of bits are there. You will be here also, you will find out. So it will be required later, but you have to find out how many types of instructions are there. So previously we have drawn one type of instruction, that is opcode, followed by this, and for this you have to calculate for 4 types or 4 categories. Okay, so try to solve this one. This is for sake of your assignment. Okay, and you have to understand the thing. Okay, why we are doing so, the step by step understanding is there, and in gate question there is no repetition. So every time when you will be facing the gate question, something new will be there. So some basic conceptual understanding is actually required. Okay, so try to solve this question. Okay, so you can have the Google form. I request you to give the attendance in the Google form, that is required. Okay, and maybe we will be solving this question in the next class. Okay. this is for your assignment. If you can solve it, it's fine. Otherwise, in the next class I will be solving this question. I will be going to the addressing mode related problems also. That is the first module of your COA GATE. Okay, so thank you. If you have any query, please ask me. Try to solve it. If you have any query, please ask me. Okay, so you try to solve it. If you do not have any query, then I am just ending the session. Okay, so thank you for being with me. If you are unable to solve, no need to worry. I will be just telling you the solution in the next class. Okay, so thank you. Please fill up the Google form also. Okay, so thank you.